Alright guys, we're going to be solving another question from the third chapter of the Meriam textbook, Engineering Mechanics. And this question was requested by one of you guys. And in order to make an adjustment, engineering students remove leg D from a laboratory work table. In order to ensure that the table remains stable, they place a 60 kilograms stack of statics books centered at point E in order to maintain the balance of this table, and we need to determine the normal reaction force at each leg. So we're going to have three legs A, B, C that we need to figure out the normal force in each, and also we have a uniform tabletop that has a mass of 40 kilogram, and we also have the mass of each leg. So I tried to draw the free body diagram for this, and I'm going to show each of the forces that we have for this table with the legs, and we're going to go from there. So first of all, we're going to have the weight of the stack of the books, which we can see in here, and that would be the point E. We know the mass is 60 kilogram, and if you want to find the force, we know mass times acceleration of gravity is going to give us the weight, which is the force that we are interested. So 6 times 9.81, and G would be 9.81 meter per square second. And this is going to give us the force in newtons. We're going to have the same story for the weight of the table at point G would be exactly at the center since we have a uniform rectangle. So that would be another force. The mass of the table is 40 kilograms. So 40 times 9.81 again. That would be our second force. We have three normal forces in each of these legs. NA, NB, NC. We don't have anything on D because we removed that leg. And also we have the weight of each of these legs, that each of them has a mass of 5. So 5 times 9.81 for each of these legs, and 1 in here. And that would be pretty much everything for the free body diagram. We have three unknowns, and we're going to have three equations as well. We are in equilibrium, so that's our assumption. And we're going to have three equations for forces and three equations for moments since we are in 3D. So we have a 3D question. So sum of all forces in X equals 0, same for Y, and same for Z. And we're gonna have the same story for moment about X equals 0, moment about Y equals 0, and moment about Z equals 0. Or if we just let's just put our origin at here at point O, and we can call this one our X, this one our Y, and this will be our Z. Or this can be turned into sum of all moment about O equals 0, which we have to do that determinant that we have for cross product of the moment, and at the end we're gonna get three equations, which is these three that we have in here. So there is a shortcut in here, and because we have all the forces in Z direction, we don't have any force in X and Y direction. So since that's the case, we won't have any moment about point Z. And we can use the shortcut that we have for finding the moment. Instead of going through this determinant, we can start finding the moment of, I'm just gonna show with this, and finding the moment of each of these forces is pretty easy. So if we look at it, we'll see that since we are trying to figure out the moment about point A, we can see that NA and NB will be canceled out because they are passing through the y-axis, so they won't make any moment. So with this equation, we can get rid of NA and NB, so that means we should be able to find the NC in here. And that's not actually hard because we have all the dimensions for finding the moment of the stack of the books. The force is 6 times 9.81, and the distance that we have. So this force about y is going to make a moment like this. So if we look at the y-axis from the point of view of this person in here, we can see the moment would be in this direction. So it would be clockwise. We're going to put a negative sign in here. The distance would be this distance, or what we have in here, 0.5. So that would be the moment of the stack of the book. Let's just call this point G, which would be the center of mass for this table, the top part. So this one's also the same direction. It will be in this direction. So again, clockwise minus 40 times 9.81. The distance, since we have a uniform rectangle, we can see the length is 2. So this would be exactly at the center of 2, or 2 divided by 1, 2 divided by 2, which will be 1. So 1 would be the distance that we have. Again, we have F and we have R. And since they are perpendicular to each other, we just have to multiply these two. So we have two more. We have the NC, which NC, as we can see, is counterclockwise. So this one's positive NC, and the distance would be the length of table, which is, I just said, it will be 0.5 plus 1.5, which is 2. And we have the weight of the leg. This one's the same direction as all the weight that we have. So again, negative 5 times 9.81 times the distance would be same distance times 2 equals 0. And we can find NC in here pretty easy. This method is going to save you a lot of time as long as we have all the forces in one direction, which is it in here. But like, if each of them has like different direction, it's gonna make it complicated. So it's probably safer to go with the determinant, but here it works perfectly. So let's just calculate everything. So we're gonna have 6 times 9.81 times 0.5 plus 40 times 9.81 times 1 plus 5 times 9.81 times 2. And we're gonna divide this. We're going to divide this by 2. And that's going to give us 259.97 newtons as the answer for the NC. We found one of the unknowns. We can do the same thing, find sum of all moments about x-axis. And if we go with x-axis, we can see that NB and NC passes through the x-axis, so no moment from these two, and we should be able to find NA. But same idea for the directions. If you look at from x-axis from the point of view of this little guy, you can see that all the weights are going to be counterclockwise, and we'll have the NA clockwise. So negative for NA. This time we'll have the other side of this, which is 0.7 plus 0.3, which is basically 1. We're gonna have the moment of the leg. This one's positive. So this one, we're talking about this one, 5 times 9.81, same distance. We're gonna have 1 again. It's just we're gonna have about x-axis. This would be our direction, which if we look at it from here, it will be clockwise. Sorry, it will be counterclockwise because this is downward. This is actually the direction. So counterclockwise and positive. Again, this would be the direction, and if I look at it, we'll see it's counterclockwise, so positive. And we have the moment of the book. This one's also same direction, 6 times 9.81. The distance would be the vertical distance from that to the x-axis, so this will be our x-axis, and this is the distance, 0.3. And we have same story for the plate of this table for the top part, and this time we can see that we have 0.3 plus 0.7, which is 1. So this distance here is 1 divided by 2, or 0.5. And because of equilibrium, this will be equal to 0, and we should be able to find NA here pretty quick. So 5 times 9.81 plus 6 times 9.81 times 0.3 plus 40 times 9.81 9.81 times 0.5, and this is going to give us 262.91 newtons, the direction for the normal force at leg A. And we have one unknown left, and that would be our NB. The easiest way to figure that one out is just to find the sum of all forces in Z direction. So as I mentioned, we don't have any force in X and Y, so actually these three won't help us at all with the moment of our point Z. So we end up with these three equations, which means we can find up to 3 unknowns. So let's just figure out what we have in Z direction. Basically, we have all the forces. So sum of all forces in Z equals 0, which means we have NA, which we found 259.97 plus 262.91 plus NB minus, one thing we can do in here, we can just factor 9.81 in here and add all the masses. So we have 6 plus 40, 46, and we have 3 legs, so 46 plus 15. Again, this is coming from the mass of all the legs. So 40 plus 6 plus 5 plus 5 plus 5 equals 0. So it's replace 61, and we can find NB here. So we can find NB in here, 9.81 times 61 minus 259.97 minus 262.91. And this is going to give us NB 75.53 newtons. And the final answer for this question. Hope everything was clear. Let me know if you guys have any questions. You guys take care. I'll see you in the next video. Have a good one.